Good morning. You guys ready to solve those structures? Did you solve them already? The ones on the spectroscopy worksheet from the last few days? There's one piece of advice that I want to give in solving it, and it is the two chicken rule. We can solve for the degrees of unsaturation by taking twice the number of carbons, less the number of hydrogens, less the number of halogens, plus any number of nitrogens, plus 2 divided by 2. And degrees of unsaturation says how many more sets of atoms could have been in a structure. So based on the number of carbons in a structure, as well as impacted by the halogens and the nitrogens, you can figure out exactly how many unique atoms could be bonded to your molecule. And if you're fully saturated, if the molecule is fully saturated, you have as many unique bonds as possible. And the ways that we lose unique bonds, I like this example. Propane, CH3, CH2, CH3. If I turn this into cyclopropane, I lose 2 hydrogens. So by losing 2 hydrogens, I'm not fully saturated. That molecule could have had more unique atoms in it. But the ring has limited the ability to have unique atoms. So rings count as degrees of unsaturation. 1 ring equals 1 degree of unsaturation. The other way that I can unsaturate this molecule is to make an alkene. If I take the CH3 and the CH2 and I double bond them, once again I have taken out 2 hydrogens. And so this pi bond says I could have had those atoms bonded to other things, but they're bonded back to each other. So 1 pi bond is 1 degree of unsaturation. And then just for a proof of concept, if I take out another set of hydrogens and I make a triple bond, I know that that first pi bond caused a degree of unsaturation. I've now unsaturated even further by adding a second pi bond. So 2 pi bonds, 2 degrees of unsaturation. Another way that I could get 2 degrees of unsaturation is, well, I'm not going to draw this one out because I feel like this is enough. Let's go back to bond line. Is if I have something like cyclopropene, which does exist. I know it's a funny looking thing, a triangle with a double bond in it. 1 ring, 1 degree of unsaturation. These are actually structural isomers of each other. They have the same chemical formula. So 1 pi bond plus 1 ring still has 2 degrees of unsaturation. The interesting thing about this equation, the 2 chicken rule, okay, and I forget if I pointed this out. Multiply by 2, subtract 2 times, add 2 times, add a 2, divide by 2. You're doing a bunch of 2's. And the way that we've laid out the letters spells chicken. The interesting thing about this is oxygen is not present. And that's because when oxygen is in the molecule, it doesn't impact how many other atoms you would expect uniquely bonding. But when nitrogen is in the molecule, you should expect 1 additional atom, which is why we add every nitrogen that's in the structure, because for each nitrogen we expect 1 additional atom. And halogens essentially just take the place of the hydrogens. So hydrogens and halogens sub out for each other, oxygen's ignored, nitrogen needs to be added in. So let's take the chemical formulas that we had, and let's calculate the degrees of unsaturation, which will help us figure out whether we have pi bonds or rings or multiples of those. C4H8O and C8H8O2. Without doing any of the math, is it obvious just from the chemical formulas whether one of them has more degrees of unsaturation than the other, or whether they have the same amount of degrees of unsaturation, whether that be 0, 1, or 2, or whatever? Is it obvious to see whether they're the same or different in terms of degrees of unsaturation? What do you think, Justice?
Well, they have the same hydrogens, but one has more carbons.
One has twice as many carbons, despite having the same number of hydrogens. So what do you think that tells you?
More degrees of unsaturation.
For which one?
C, the second one. C.
For having twice as many carbons, you would think that it should have twice as many hydrogens as well, because it's going to have a very large number at the front. But for having the same number of hydrogens, it must have more double bonds and rings in some combination in order to have such a few number of hydrogens. All right, so we plug it in. We get 2 times 4 minus 8 minus 0 plus 0 plus 2 divided by 2. 8 minus 8 is 0. So I'm really just doing 2 minus 2. This compound either has 1 pi bond or it has 1 ring. How can I verify what it is? 1 pi bond or 1 ring? Can't really. From a chemical formula, there's no answer. Cyclopropane and propene have the same chemical formula. You can't say which one, whether it has a ring or a pi bond, just based on a chemical formula. Propyne and cyclopropene have the same chemical formula. So once again, we can't really say whether this shows up as a ring or a pi bond. But we can look at the data. We can look at its spectra. Here, I've got 2 times 8 minus 8 plus 0 minus 0 plus 2 divided by 2. 16 minus 8 is 8. Plus 2 is 10. Divided by 2 is 5. So Justice, you were right. The one that had twice as many carbons but the same number of hydrogens was a lot more unsaturated. It could have had a lot more atoms in it. When you see degrees of unsaturation that large, there's usually an aromatic ring in the structure. So we pulled out some information yesterday from these spectra about our compounds. Now we're going to combine all of it. For the one on the left, can you guys remind me what the IR told us about the molecule? What bond types were present? Oh, well, we don't know that, do we? We did. We figured it out, right? We said its molecular mass was so small compared to the other one, which had a much bigger molecular mass. No, we didn't really agree to that, did we?
Wait, are they all on?
Yes, yes. All the spectra on the left are one compound. All the spectra on the right are one compound. So because the mass spectrum on the left had a smaller molecular mass, what was it, 72? Yeah, I think we went through and we proved that this was the correct chemical formula. 4 times 12, 48, 56 and 16, 72. So this chemical formula agrees with the mass spectrum on the left. What did the IR tell us about this compound? sp3ch. What else?
Some sort of.
Yeah, we've got a carbonyl. We didn't see any evidence of a carboxylic acid. Our chemical formula does not allow us to have an ester. We didn't see great evidence of an aldehyde. We didn't see the twin peaks at 2800 and 2700 wave numbers. So that really means ketone. Maybe it's a ketone. What about the NMR? What did the NMR tell us about this compound? Oh, we didn't finish going through NMR. That's what we had to start with today. Dang it. Okay, nobody caught my 8 a.m. brain lagging, which means all of your 8 a.m. brains are lagging too. How long ago did you guys start waking up at 8 a.m. or 7 a.m. or whatever to be prepared for this 8 a.m. class?
I had OChem 1 at 8 a.m. over at UVU too, so I woke up at the exact same time.
But just in the spring?
Yeah.
Okay, so you've been in the habit.
Yeah.
Good for you. I tried getting in the habit of waking up early last week. It didn't work very well. Okay. Let's keep talking about NMR. We had 2 other things to talk about, right? Integration. Those of you that have taken calculus know that the definition of integration is area underneath a curve. And that is exactly what it is here. Old NMR instruments would give a signal, and they would calculate the area underneath that curve of that signal. And what they found is that the integration is exactly equal to the number of hydrogens producing that signal. We should expect that unique hydrogens give unique signals, and a unique hydrogen is any hydrogen that doesn't share a similar environment to something else. CH3 hydrogens are not unique to each other. A CH3 has 3 hydrogens that all produce the same signal, so a CH3 will produce a signal that integrates to 3H. CH2s, similarly, CHs, unless there's some symmetry in them. So if we find 2 CH2s that have some symmetry between them, these are not unique hydrogens. They're actually all the same hydrogen, and so their signal, they all produce the same signal, and their signal integrates to 4H. So the integration tells us how many unique hydrogens. The fun part is that signals can overlap with each other. So sometimes unique hydrogens give unique signals, and those unique signals are just too close to tell apart. So you can't really tell that they are unique. There is the issue of overlap. In which case, you can still get the total integration, and you can see how many hydrogens are making all of those signals, even if you can't see how many signals specifically. The last component is splitting pattern, and in my opinion, this is a feature that you need if you are an organic chemist or a spectroscopist. This is not something that you need if you are in OCHEM 2. You don't really need to be able to interpret the splitting pattern. The way that it works is simple enough. The number of peaks that a signal presents with is equal to the number of neighboring hydrogens that those hydrogens have plus 1. Neighboring hydrogens, we say, are hydrogens on adjacent carbons. If a set of hydrogens have no neighbors, 0 plus 1, they still need to have a peak. They still need to have a signal. So 0 neighbors, 1 peak. But as soon as you start having multiple neighbors, you get doublets and then triplets and then quartets and quintets and sextets and septets. And it can get really complicated, but usually past 5, the number of peaks gets really hard to discern. They become smaller and more crowded. So this isn't something that I feel you'll probably have to lean into that much. But it can be a useful structural tool. It can tell us whether I have a signal from 3 hydrogens that are being split by 2 hydrogens into 3 peaks, and a signal of 2 hydrogens that's being split into 4 peaks by 3 neighbors. Those signals are related to each other. They are splitting each other. I guess it would make sense for me to have the spectra pulled up while we look through this. So with that in mind, what we can glean from the NMR on the left, we've got 3 hydrogen regions. We have a CH3, a CH3, and a CH2. None of which agrees with having an aldehyde. So we're using some feedback between IR and NMR to say, I wasn't sure if I had an aldehyde in IR. NMR does not support the idea of an aldehyde, so I don't have an aldehyde in IR, in which case that IR signal probably comes from a ketone. And a ketone won't show up on the NMR, because a ketone carbon has 0 hydrogens bonded to it. So I've got 4 carbons in my structure. I've got 3 hydrogen groups in my NMR. Where's that last carbon? It's the ketone carbon. Why is it taking so long to switch over? The other thing that we can glean from this is chemical shift. Oh, my integrations are wrong, and I didn't catch that. This CH3 on the left should be a 2H, and this 2H should be a CH3. Sorry. Yeah, that was silly. I don't know why I made that mistake. I will say the data that I'm giving you and the data that I will always give you with spectra comes from the Japanese Spectral Database, SDBS. So these are real reported spectras. They're not simulated spectras, but they don't come with integrations. I give that to you, and I make mistakes sometimes. So we know that we have these groups. We've got two CH3 groups, and we've got a CH2 group. The splitting patterns and the chemical shifts tell us a little bit more. The chemical shift of the CH3 around 1 says that this is predominantly alkane region. It's not bonded next to a functional group. It's not bonded next to anything special. It's just bonded to other carbons, other alkane carbons. Then I have these two signals that are left of 2 ppm. Those are functional group adjacent. But if you remember on our correlation table, which I didn't bring again, on your correlation table, we saw that things that are adjacent to a carbonyl show up a little bit closer to the right-hand side of this region, and things that are adjacent to an oxygen show up further to the left on this region. So because my signals show up closer to 2, I suspect they're closer to a carbonyl. Well, that makes a lot of sense because I have a carbonyl in my structure. So 2 of these are next to a carbonyl. And that carbonyl, again, won't show up in the NMR because the carbonyl doesn't have a hydrogen attached to it. So these have signals near 2 ppm. That's next to a carbonyl. This has a signal near 1 ppm. That's just alkane. The other thing that I can take about this, that CH3 near 1 ppm has 3 peaks. 3 peaks would tell us that it has 2 neighbors. Where are those 2 neighbors? Well, I have a CH2 that has 4 peaks, which means that it has 3 neighbors. They're probably neighbors to each other. The reason that one signal is split into a quartet is the same reason that the other signal is split into a triplet. And my last CH3 is a singlet, which means that it has 0 neighbors. I have a CH3 next to a CH2 next to a CO, and that CO is also next to a CH3. Do you guys see the structure yet? Do you know what it's called? Can you describe it? Do you see how it pieces together? Is it still a puzzle? CH3, no neighbors, singlet, next to a carbonyl, chemical shift is past 2. CH2, 3 neighbors, shows up as a quartet, next to a carbonyl, chemical shift is past 2. CH3, 2 neighbors, shows up as a triplet, next to alkane, shows up at 1 ppm. There's our structure. Fun stuff, right? Okay, what did IR tell us about the spectrum on the right? And I know more of you than just Jordan can answer this. We did. Sorry? Carboxylic acid. Those two things aren't the same. Right, which is not an alcohol. Right. Do you guys ever watch The Good Place? You guys know Janet? Janet from The Good Place? That like AI, what does she call herself? Resource. You just say her name and she pops up with anything that you want. And later in the series, Jason keeps calling her a girl, and she's like, not a girl. And that's how I feel when people call this OH an alcohol. I'm like, not a girl, not an alcohol. It's close, I get it. It looks like it. Just like Janet looks like a girl, not a girl. Okay, so we've got the CO double bond and the OH of a carboxylic acid. How can we be so confident? that the CO double bond and that big OH both belong to a carboxylic acid. Maybe the OH only belongs to the carboxylic acid. Maybe the CO belongs to, the CO double bond belongs to something else. This is what I refer to as a corresponding peak. If I have the OH of a carboxylic acid, I will have the CO double bond of a carboxylic acid as well. I can't have one without the other. Like when I had the CO double bond on the left, but no OH of a carboxylic acid, no H of an aldehyde, no CH of an aldehyde, I knew that that CO double bond couldn't be from an aldehyde or a carboxylic acid because it lacked those corresponding peaks. But here, these are both corresponding peaks to the carboxylic acid. We also believe that there was carbon-carbon double bond. Although we felt like we were lacking the sp2ch of that carbon-carbon double bond. Maybe it got swallowed up by the OH of the carboxylic acid. We felt like there was evidence of a CC double bond, but didn't feel like we saw that corresponding peak. In the NMR, we said that the chemical shift told us we had some functional groups. This signal close to 13 ppm was in the same region that we would expect aldehyde or carboxylic acids to show up in, and we felt we had more evidence of a carboxylic acid. So NMR tells us that we have a carboxylic acid. NMR also told us that we had an aromatic ring. And that aromatic ring is not a complete aromatic ring. Because of its integration being 4H, we know that this aromatic ring is missing 2 of its hydrogens. It's got 2 groups connected off of it. Here's what I'm going to do. I'm going to say R1 and R2. I know that there are 2 groups, but are those 2 groups adjacent to each other, 1,3 to each other, or exactly opposite, 1,4 to each other? That don't quite know just by knowing that there are 2 groups off of it. I don't know the relationship. But the splitting pattern of this signal can actually give a really nice clue. The fact that the splitting pattern is this clean doublet and doublet, and it integrates to 4H overall, but those integrations of those 2 signals look pretty well matched, 2H and 2H. This means that I've got 2 identical hydrogens being split by just 1 neighbor. 2 identical hydrogens, 1 neighbor each. That means that I'm going to have a plane of symmetry in my aromatic ring. 2 hydrogens identical to each other with 1 neighbor on either side. This shape suggests a 1,4 distribution of those 2 substituents. Rather than 1,2 or 1,3, these groups are exactly opposite each other. And then the NMR tells us that we've got a CH3, no neighbors. So we know what the 2 groups are coming off of the aromatic ring, don't we? This is all of the evidence that I have from the NMR. And I don't know what these 2 groups are, and I don't know where these 2 groups go. Well, that's hand in glove, right? 2 groups missing, 2 groups without homes. It really is the idea that the aromatic ring is 1,4 substituted that tells us everything that we need. The CH3 and the carboxylic acid are attached off of the ring 1,4 to each other. In a class like this, if you gave me one of the structural isomers, I would give you partial credit, if not full credit, because I've told you that this science is a bit hand-wavy. that these signals overlap, and that can cause some trouble in reading them. The aromatic, the alkene signals, they often are really messy signals to read. So if you read that and said, oh, it looks like I'm being tricked, it can't be as simple as two symmetric hydrogens being split by two symmetric hydrogens. It can't be that easy. Sometimes it is. So if you gave me something like this, I would give at least partial credit. I probably would give full credit on a test, although I don't know that I've ever given a structure quite this hard on a test. Again, usually when you are given spectra on a test, it's a bonus problem anyways. So I'd be looking to see that you can pull out a lot of that information, like there's an aromatic ring, there's a carboxylic acid, there's a methyl group. That's a lot of information to pull out already. How fun was that? Spectroscopy, so cool. If you don't think spectroscopy is cool, then just close your eyes and stop looking at stuff, because spectroscopy is just manipulating light to look at things. It's just we're manipulating non-visible wavelengths of light. So if you don't think spectroscopy is cool, you must not think looking at stuff is cool, so close your eyes. Okay, I have one last worksheet for us today, and this will get me to shut up a lot more, so you guys will have more time to just work on stuff and practice. I have not added this to Canvas yet. I knew it was coming. But I didn't know it was coming earlier when I got here early, so I only knew because you were here. Thank you. Thank you for doing that. On this worksheet, we have some resonance that I want to talk about, hybridization that I want to talk about, and then some practice problems. Have you fill in a roadmap, filling in reagents and products. Have you solve some syntheses, and then have you solve a chemical structure again, but this time using, I'm so close with my words, using spectra, but you're given a chemical formula. So same thing that we're just doing, but a little bit different. I'm going to upload this to Canvas real quick, and then I will start us on resonance. Feel free to look through it and just start filling in things that you recognize. I would really recommend doing the roadmap and the synthesis with those reactions that I gave you guys. Okay, this one is on Canvas under Unit 1 as resonance and synthesis. Let me know when you're able to access it, Jordan.
Thank you.
Good, you're welcome. All right. Did we talk about resonance? No. You love resonance?
Yes.
Can you define resonance? I've never heard someone say yes, they love resonance, but no, they can't define it.
Isn't it, I don't know the exact definition, but I want to say it's but it's kind of moving them around, and so the structure will just constantly be switching between. Or I guess it goes into a hybrid of the two, or multiple structures.
That would be a lengthy definition if we went with that. But you are on the right track. There's a stabilizing factor to it. The electrons are moving around. The electrons aren't actually moving around. It's just some hybrid of all of these different structures that we have. Do you guys use resonance or like derivatives of that word resonance ever outside of chemistry? Do you have an idea of what it would mean outside of chemistry? That really resonates with me. Right? Like, you just told this story and wow, same. Same but different. I think of opera singers a lot. That idea that opera singers can hit the resonating frequency of glass and shatter the glass. That tells you that glass molecules are vibrating. And if you hit them with sound waves that match that frequency, you can get them to vibrate further and further until they just shatter. That's their resonant frequency. Something resonates with you, you are the same, it's the same but different, and that is what I think of with resonance. Things that are different but actually are the same. The way that I like to define this is that it is the movement or delocalization of pi electrons. And I say both movement and delocalization because it depends on what perspective you have on it. If you have the perspective of Lewis structures, it looks like movement. If you have the perspective of MO theory, it looks like delocalization. And MO theory is a better descriptor of what electrons are actually doing. But Lewis structures just help us understand how the whole thing comes together. So they're both useful ways to visualize resonance, and I'm going to demonstrate both of them for you. First, I want to give you the rules for resonance. There are 3 rules that contribute or help you define contribution of a resonance form. The first rule is that we want to minimize charge. A resonance form that minimizes charge is a major resonance form. Take this for example. When I'm teaching general chemistry, I have students that try to draw out trifluoroborane or boron trifluoride, and they're aiming for the octet rule. So they think that they should draw this compound so that boron has a full octet. What they don't do, and this is something I'm actively trying to change in our labs especially, what a lot of instruction doesn't do is teach about formal charge before they teach about electron deficient atoms. And we can prove that this structure on the right is a worse structure because it puts a negative charge on boron and a positive charge on fluorine. I have maximized the octets for boron, but at the cost of having 2 charges in my structure, and a better contributor to the molecule is the one that has minor charges. So we say that this is more stable, or we say that it's a major contributor. The other 2-atom system, and this will have more relevance for us in OChem, is looking at a simple pi bond and breaking it, moving the electrons from a shared position, moving them into a localized position, moving them off of the carbon-oxygen double bond, moving them onto oxygen selectively. Which of these resonance forms is a major resonance form? The one on the left, because it has minor charge or minimum charges. It has no charges. Major contributor. By the way, this is what I refer to as the two-atom system, where you simply have two atoms that you're moving pi electrons between. Okay, rule number 2. By the way, not all of the rules that we have in chemistry go in order. These do. Rule number 1 is the most important. Follow rule number 1 first. Then think about rule number 2. Rule number 2 is maximum octets. The next major resonance form is the one that maximizes octets. You can see how these can't be swapped, right? Because this structure with the borine-fluorine double bond, borine-fluorine, what? The boron-fluorine double bond does maximize octets. That's why this is the second rule. If charges are minimized, then try to maximize octets. But if you can't minimize charge in order to maximize octets, it's better to minimize charge than maximize octets. Okay, so here's another two-atom system. This is the one that you guys have at the top of this structure, at the top of this new worksheet, sorry. Another two-atom system. This time it's an atom that has a vacancy, the carbocation, and an atom that has an excess, a lone pair on the oxygen. So we can show the electron arrows. I didn't really show the arrows here, but this is what these would look like. We can show the electron arrows taking one lone pair from oxygen and satisfying the octet on carbon, placing that positive charge on oxygen instead. Two-atom system. It looks very reminiscent of this first two-atom system, but in reverse and without changing charges. One positive charge on the left, one positive charge on the right. Net neutral, but no charges, two charges. So charges are conserved. Charges don't change, right? But I have maximized octets. Carbon was lacking an octet. Now carbon has an octet. Oxygen had an octet. It still has an octet. Do you disagree, Mimi? Does it surprise you that oxygen has an octet?
Kind of. I see it because of the other lone pair, yeah. My only question is,
2, 4, 6, 8.
does that mean now that, like, this structure on the left is going to be the major contributor, though, wouldn't it be?
Why?
I'm thinking because of the, I feel like carbon can better handle a positive charge versus
Look at the rule, though. Look at the rule. I'm not interested right now. Whoops, I put an exclamation point instead of an I. I'm not interested right now in where is the positive charge held better. I'm interested in what? Maximizing octets. If carbon lacks an octet, that's not the best resonance form, despite how uncomfortable that can feel. Actually, if it feels uncomfortable, that means that you have developed chemical intuition. You have an intuition about where a charge should go. And when that charge looks like it's in the wrong spot, it starts to feel uncomfortable. If you don't feel that uncomfortability, that's okay, but recognize that it means that you can work on developing your chemical intuition. Positive charge on a less electronegative atom makes sense, but it breaks an octet. Do you know how many atoms regularly lack an octet because they maybe have a charge? Just carbon. Boron lacks an octet when it's neutral, so that's kind of an odd case. Carbon lacks an octet when it has a positive charge. None of the other atoms that we regularly deal with lack octets, ever. So when we say maximize octets, another way of saying this is maximize bonds to carbon. Make sure that carbon has all of its bonds. Give carbon 4 bonds. Yes, Mimi, even at the risk, or at the, is it risk? At the cost of putting a positive charge on oxygen. Give carbon those 4 bonds. Now, rule number 3, appropriate charge placement. Do you remember how we couldn't have satisfied rule number 1 if we were paying too much attention to rule number 2? We would have gone with this structure for BF3 because we focused on rule 2 instead of rule 1. This is what you were getting at, Mimi, with if we'd focused on rule 3, putting the charge in an appropriate place, we would have been skipping over rule 2. And rule 2 is more important, which is why it's rule 2. So I want to give us the next structure, which is this 5-membered ring, nitrogen, oxygen, and a carbocation. Now this is going to look like a 2-atom system at the start, but we're going to have 2 additional resonance forms. And once we get to the other 2 resonance forms, we'll see how it turns into a 3-atom system. First, let's show the same thing that we saw before. Oxygen adjacent to a carbocation can share a lone pair. When oxygen shares a lone pair, it makes a double bond, but takes on the positive charge. Now I want to introduce you to the 3-atom system. A 3-atom system typically has 1 pi bond and a charge or lone pair, sometimes both. And the 3-atom system here is the pi bond between oxygen and carbon and the lone pair on the nitrogen. In the 2-atom system, we only had those 1 arrow showing a bond forming or a bond breaking. But in a 3-atom system, you can have more arrows. Sometimes it's just 1, sometimes it's more than 1. And the way that electrons should flow, the way that we should have our arrows drawn, is towards a positive charge from a region with more electron density. So in this 3-atom system, I'll take the lone pair from nitrogen to make a pi bond, and I'll break the pi bond off to oxygen. Form a pi bond, break a pi bond. In this new resonance form, this final resonance form, it is nitrogen that holds the positive charge. What Mimi brought up earlier about more than 1 resonance form, but not any of them being exactly the right structure, is the idea of a hybrid. This structure's hybrid could look like this, where we have this, actually I'll even draw this as a dotted line, where we have this partial double bond character between those 3 atoms and a positive charge that is delocalized somewhere. There is no single bond CO, there is no double bond CO. It is both single bond and double bond all the time. It's bond and a half. And we have instruments that can measure bond length, usually X-rays that are helping us measure bond length. And if we measured that bond length, we would not find that it's 1 CO bond length or a CO double bond length, but it is somewhere in between those bond lengths. So this is the resonance hybrid. These are the resonance forms, which of these 3 resonance forms is the major contributor to the molecule?
The middle one,
Tell me why.
because they're also satisfied with their octet.
Not all of them are satisfied with their octets. We can actually rule out rule 1. All of them have the same charge. But there is one of them that does not satisfy all octets. There's one with minimum octets, or one without maximum octets. You guys know?
I was going to say the very right one is the most stable.
Okay, tell me why.
The positives on the nitrogen instead of the oxygen or the carbon.
Where does a positive charge go better? On a less electronegative atom. And nitrogen is less electronegative than oxygen. So this is our major contributor. But Mimi, let's touch back. Have we found the one that doesn't maximize octets? Or in other words, the one that doesn't give 4 bonds to carbon? The first one doesn't give 4 bonds to that carbocation. So this is a minor resonance form. The most minor resonance form. The least stable, if you will. The one in the middle at least maximizes octets, but it doesn't hold the charge quite as well as the nitrogen. If we had a negative charge between an oxygen and a nitrogen, the negative charge would go better on the oxygen. But because we're seeing a positive charge delocalized, the positive charge goes better on N. Okay. I want to talk about MO theory, but before I do, in this realm of structures, I also wanted to make sure that we had talked about hybridization and bonding. So let's take that top right resonance form, and let's talk about some of the hybridization that's in here. Is it easy enough for you guys to identify hybridization? What is the hybridization of the oxygen in that molecule, that blue molecule? Esmeralda? Nice. How'd you do that? Including the assumed lone pair. 2 bonding regions, 1 non-bonding region. Count up from S into the P's, SPP. sp2 oxygen. How many carbons are sp2? Jordan's trying to secretly sign to me that she's got 1. 1 of the carbons is sp2. What are all of the other carbons? sp3. All of the other carbons are sp3. Beautiful. Actually, it's really cluttered, isn't it? Okay, so I'm going to erase some of that because it's too cluttered for me to do what I wanted to do next. What I want to do next is talk about what bond overlaps or what orbital overlaps give us the bonds that we have. So if we look at the CO double bond, every bond has a sigma bond. Every bond has 1 sigma bond. So this CO double bond has 1 sigma. All of the remaining bonds are pi bonds until you get into transition metal chemistry, and then you can have sigma, pi, and delta. But here we're limited at sigma, pi, maybe sigma, pi, and pi. What orbitals are overlapping to give me the sigma bond here? Hybridized orbitals give sigma bonds. Unhybridized orbitals give pi bonds. So what orbitals overlap to give me this sigma bond? What are the hybridized orbitals from these two carbons, these two atoms? SP? No. They don't have SP orbitals. They have sp2 orbitals, right? Both the carbon and the oxygen have taken 3 of their atomic orbitals, turned them into 3 new types of orbitals identical to each other, all sp2. sp2, 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 and they'll use one of their sp2 orbitals to make this sigma bond. What orbitals are overlapping to give their pi bond? P orbitals, unhybridized p orbitals. P for pi, that is an intentional alliteration. What about this bond between C and O on the right? That's also a sigma bond. What orbitals are overlapping to give that sigma bond? And? No. Because oxygen doesn't have an sp3 orbital. Good try. So, one more time.
sp2 and sp3.
Do you guys see that? The hybridized orbital from oxygen, sp2, is overlapping with the hybridized orbital from carbon, sp3, to give that overlap to make that bond. Carbon only has sp3 orbitals to use. Oxygen only has sp2 orbitals to use because its p orbital is already used in pi bonding. What about this last one? What orbital holds oxygen's lone pair? P is used. Oxygen has no more P's to give. It had S. It had 3 P's. Those were its atomic orbitals. It took 3 of them and it made hybridized orbitals. It left 1 unhybridized P, and it's using that P orbital to pi bond. So it only has those 3 hybridized orbitals to use. One of those hybridized orbitals makes a sigma bond. The other makes a sigma bond. So where is the third sp2 orbital? And where is that lone pair? It's in that last sp2 orbital. We call sp2 orbitals sp2 because it is a very good description of what those orbitals are. An sp2 orbital is the combination of s with 2 p's. But you don't take the combination of s with 2 p's without getting 3 orbitals back. If you have 1 sp2 orbital, no you don't, you have 3. All 3 of them have to be used somewhere, somehow. If you have 1 sp3 orbital, no you don't, you have 4. Because to make 1 sp3 orbital means to use s, p, p, and p, and so there must be 4 copies of it, right? Okay, what about the overlap of the CH bond down here? It's sigma, of course, because every bond is a sigma bond until you have multiples and then they're pi's. What orbitals are overlapping to give that sigma bond? Hydrogen only has S, and that carbon is sp3. So we're looking at an S and sp3 overlap. What is this blue structure relative to the blue structure we just did? It's a resonance form. Which of these resonance forms exists? Resonance forms don't exist. They're figments of Lewis structures. So these are the same molecule, just a different perspective. Same molecule, different perspective. Say that back. Same molecule, different perspective. What's the hybridization of that oxygen? Okay, hang on. 30 seconds ago, I had you guys speak at me. What did I have you say? Same molecule, different perspective. What was the hybridization of oxygen above? What is the hybridization of oxygen below? Yes. Resonance forms don't exist. So the hybridization of one atom in one resonance form is the same as its hybridization in another resonance form. I know that oxygen looks sp3 because, as Meralda just told us, count up the electron regions. 2 lone pairs, 2 non-bonding regions, 2 bonding, that's sp3. But we just looked at a resonance form where that was not true. So which one do we believe? If resonance is the movement of pi electrons, and if we're saying that we see this electron move, then what is this lone pair? It's pi electrons. It doesn't look like it's pi electrons, does it? It looks like a non-bonding lone pair in an sp3 orbital. But because resonance is the movement of pi electrons, and these electrons are moving, these must be pi electrons. And pi electrons are held in p orbitals. That's how we make pi bonds. What orbitals overlap to give this sigma bond? sp2 and sp2 and sp2. Because guess what? It's not a different sigma bond than the structure above. Because resonance doesn't move sigma electrons, resonance moves pi electrons. Yeah? So resonance is not moving the sigma electrons, and if the sigma electrons were the overlap of sp2 and sp2, then the sigma bond is still the overlap of sp2 and sp2. Then what about these 2 lone pairs? One of them we said was held in an sp2 orbital. That hasn't changed. One of them is held in an sp2 orbital. So this oxygen, despite looking like it's sp3, we know it's sp2 because of its resonance form. So it has an sp2 orbital to sigma bond, an sp2 orbital to sigma bond, an sp2 orbital to hold the lone pair. What is this lone pair held in? A p orbital, because it's pi electrons, which we see because it's moving. I love it. Don't you love it? Isn't that awesome? It was all a lie the whole time. You can't just count the electron regions. It's never that simple. Well, 90% of the time it is, unless it's resonance based, in which case it's not that simple. Cool?
In that case, would you just go based off of the hybridized structure?
Well, yeah, the hybridized structure, we know that this is the major contributor. So the resonance hybrid looks mostly like this.
It would just be that number one would be like.
You have to be able to say this structure is capable of resonance. Therefore, it must be capable of resonance. If that lone pair is not in a p orbital, then that lone pair is not pi electrons, then that compound is not capable of resonance. But since we know that this compound is capable of resonance, then this lone pair must be in a p orbital in order to do the resonance. It's kind of like a deductive reasoning more than based on all of those tricks that we learned in Gen Chem.
Is this going to be like on an exam question? If it has a resonance, we have to find the major and then find the orbital?
Well, yes, I think on your unit test you will see some questions that talk about orbital overlap. So I want you guys to be able to predict hybridization and make orbital overlap predictions. But actually, next week, we're going to spend a lot of time talking about this. Why is that oxygen sp2? So this is actually a little bit more of a preamble for next week, more so than it is something you'll see on the test this weekend. You will have to do resonance this weekend on the unit test. One of the reasons I have it on the packet is because I want you to do resonance with it. I want you to know how to do resonance. But not like this until next week. On the final, you'll see a question like something like that. Okay, that last molecule on our resonance has two other resonance forms, but only one other major resonance contributor. I want you guys to determine the other major resonance contributor, use the 3-atom system idea, and figure out if they're equally major resonance contributors or whether one is more major than the other. In the meantime, are you guys all right if I erase the board? Yeah? Okay. Find that missing resonance form and determine if it's more major, more minor, or equal. Find it? Did you guys get something like this? The double bond moves to the other OH. Positive charge moves to the other O. More major, more minor, equal. You can do it in one step. If you use the 3-atom idea, you can move a lone pair and a pi bond at once. You can do it in 2 steps. If you use the 2-atom idea, break one pi bond, make a less major form, then reform one pi bond. Yeah, and the intermediate where you have a carbocation, that would be the most minor form. But these two would be more major. Are they equally major? Yeah, they're practically identical. Okay, now I want to talk to you about how MO theory depicts resonance. Here we've been showing movement of electrons. Take an electron arrow, move the electrons somewhere else. But MO theory says that electrons are delocalized. They're not moving because they're already there. So in this 3-atom system, I know that this oxygen looks like it's sp3. We can use our rules. 2 non-bonding pairs, 2 bonding pairs, sp3 hybridized. But we know that it's in a resonance form, so it can't be sp3 hybridized. It must be sp2 the whole time. That means that I have an unhybridized p orbital on all 3 of my atoms at the same time. So MO theory will take those orbitals, and rather than giving you localized bonding, a double bond between these 2 atoms, and then a double bond between these 2 atoms, MO theory will take that series of p orbitals and say, I can take 3 orbitals in and pump out 3 new orbitals out with new characteristics spread across the molecule. The lowest energy is when all 3 of those orbitals are in phase with each other. Constructive interference between the oxygen, carbon, oxygen. And these are p orbitals. And it doesn't need to be oxygen, carbon, oxygen. It could be carbon, 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 nitrogen, oxygen, nitrogen, oxygen, nitrogen. There's so many combinations here. That's not actually the one I wanted. Oxygen, nitrogen, carbonate. Oxygen, nitrogen, oxygen. There's so many combinations, but what I want to draw your attention to is that there's a nucleus at the center of each of these. So molecular orbital theory says if I have these unhybridized p orbitals, they could all 3 come together constructively. They could all 3 come together destructively. There would be 2 nodes in this highest energy molecular orbital. A node is where electrons are not found, but more importantly, a node is where a wave changes its sign. If you think about a wave in the ocean, the node would be right where that wave is technically at normal sea level. Is there really a wave if the water is just exactly where it's supposed to be? Not really. There's not a wave there until it starts moving up or down, but as it goes between, there's no wave. Here's a node, because our wave changes sign, and the electrons are not found there. So how do I go from 0 nodes to 2 nodes? I must have an orbital in the middle that has 1 node. And nodes find themselves symmetric. That sounded weird. Find themselves symmetrically in a structure. So this 1 node is going to have to go in the middle of the structure. Remember that there were 3 nuclei in our bottom orbital, 3 nuclei in our top orbital. There are 3 nuclei in our middle orbital as well. You just can't see it because it started turning purple. Guess what? The node falls over one of those nuclei. That's okay. That just says the electrons are never there. Now let's fill in electrons from this system. These are only pi electrons. I'm ignoring sigma electrons. I'm focused on the pi system. There's obviously 1 pi bond. So those electrons are going to have to fill in. But there's also a lone pair from this other oxygen that is moving in to make a second pi bond. So I have 2 sets of pi electrons. I've got these 2 pi electrons, and I've got these 2 pi electrons. So let's fill in the pi electrons from lowest energy to highest energy. The lowest energy fills into the pi orbital that spans all 3 atoms. The next lowest energy fills into the molecular orbital that only sits over the oxygens. These electrons are never seen by the carbon. Lewis structure says the pi electrons are moving. MO theory says, no, they're not. MO theory says that there is 1 double bond across both oxygen, carbon, and oxygen. There is 1 pi bond spread across that whole region and a positive charge delocalized. MO theory also says there's a lone pair that is held on both oxygens, but is never held by the carbon. And our Lewis structures kind of agree with that. But it doesn't look like this lone pair is this lone pair. These look like different electrons. That's the limitation of Lewis structures. Lewis structures suppose a more localized bonding, and so just a movement of different electrons. MO theory says those are not the electrons you think you're looking at. MO theory says this lone pair and that lone pair are actually just oscillating between the two oxygens.
How do you know, like if you were just looking at the MO theory diagram, how would you know which ones are like the lone pair and which ones to the bond?
Yeah, good question. So because these are delocalized across 3 atoms, and because they're the lowest energy, these would be the bonding electrons, whereas these are non-bonding. This is anti-bonding, but here you have like essentially neutral energy, net zero, not stabilized, not destabilized. So these are actually non-bonding electrons. Good question. How would you know? It takes practice looking at it a lot. This is going to help us a lot later in the semester as well. We're going to understand how MO theory can predict resonance and how resonance can help predict stability. Especially next week with aromaticity. Isn't it beautiful? Really though, like Lewis structures look confusing. We got confused about our hybridization. MO theory says, you think that's confusing? Hold my beer. Okay, cool stuff. Now, actually, Ju had drawn a resonance form that I didn't draw up here. And I don't know why I didn't draw my other line. But Ju had drawn this resonance form as well. And that resonance form isn't really shown here, other than the fact that it reminds us the carbon doesn't get those electrons. The 2 oxygens each get a lone pair, but the carbon never gets those electrons. Which, again, is why this is a minor resonance form. MO theory doesn't really say you should ever draw anything like that. MO theory says you should draw something like this. But MO theory also says there's 1 lone pair here, and that's really hard to draw with a Lewis structure. It's hard to draw 1 lone pair at 2 different places. So we don't use MO theory to draw a structure because MO theory does a really good job looking at a nice isolated system. Lewis structures do a good job showing us the rest of a molecule in its entirety. We'll use both. They both have simplifications. Was that fun? Well, I said I wasn't going to talk the whole time, and then I just couldn't get off resonance. So the rest of the time is yours. I think the spectroscopy at the end is fun, but I would say that this resembles more of the bonus problems that you will have on a test than any graded problem, whereas synthesis and the roadmaps are a lot more similar to what you would be doing. Maybe not, you're not filling out a synthesis or a roadmap on the test this weekend, but on an exam, on the midterm exam, you'll be doing stuff like that. So the rest of the time is yours to work on them. Ask me questions, work together, collaborate. The rest of the time is yours. And the unit test opens tomorrow. Tomorrow at like dawn. Midnight a.m. You know what I mean? Doesn't open tomorrow at midnight. Opens tonight at midnight. That's a better way of saying it. Finish them already?
No, I'm
Oh, you're just...
trying to comprehend it.
Yeah.
Because remember I told you this is like my big weak spot. So I'm like,
Well, I would say it's everybody's weak spot. I think that MO theory is a more complicated language than Lewis structures. Resonance forms aren't that hard to grasp. They're challenging, but they're not as hard as MO theory. MO theory has a lot of math component to it.
so did the 4 electrons that are on like these guys, these 4,
Yeah,
are those representing the pi electrons?
they are the pi electrons. They are these pi electrons. The one that is obviously a pi bond and the one that is pulled in to make a new pi bond. You've done this one already, haven't you? No?
Maybe. I don't. Is it?
I thought maybe you guys practiced with it.
Practiced it?
It's from an old final exam, yeah.
If it wasn't like just the last one before it.
Oh, okay.
I didn't do it.
What have you done in this step?
Taking away that nitrogen.
Just a hydrogen? Is there anything else bonded to that carbon?
Yeah. Well, this one has hydrogen.
Okay. And is that still there then?
No.
What do you mean no? Because you said you took this hydrogen.
Yeah, I know. That's,
So I would say it's still there.
uh-huh.
In which case,
It can't be there. That's what you're saying.
or something else needs to leave.
Well, no, that can't be the case. Right?
Elimination has
Go this way.
another name. Dehydrohalogenation.
So just get rid of.
D meaning remove, hydrogen. Halogenation. You need to remove both an H and an X. You left your X.
Okay. You don't. So you do remove both.
You got to get rid of both. That's the usefulness of the alkyl halide. The halogen acts as a leaving group.
Got it. That makes sense.
Good. If you worked backwards on that, you know how this is formed by an alkene. You wouldn't have known how this forms with one halogen already in it. It would have been kind of weird.
Yeah.
Mm-hmm.
Okay.
Two.
I am stuck on that middle. I know how to do the other ones.
This one here? Well, this is,
I was like thinking, is it substitution?
it could be substitution, but tert butoxide
Oh, that's what it is?
is a really good base.
Okay.
Mm-hmm.
Just taking that BR out.
The tert butoxide is actually taking an H off, but the removal of the H means carbon gets an extra lone pair, and that carbon doesn't want a lone pair, so carbon shares it with its neighbor and kicks off the bromine. So by tert butoxide removing an H, the bromine is allowed to leave the molecule as well. Antizative elimination.
Is that it?
Yep.
I was seeing that as like R O H.
This is not ROH, RO minus, but specifically it's TBUO minus, which is our big bulky antizative base. An alkane in HBr won't really react.
Oh.
You'll need some other way to get that bromine on there.
Radical bromination.
Mm-hmm.
I don't know what that one was.
Do you have the packet?
Yes.
Because you won't get that packet on the midterm, but it's a useful way to get familiar with all the reagents before the midterm. You guys are okay if I erase this all, right?
Sorry.
Tell me.
The IR and the NMR chart, are we gonna have that on the midterm?
Yes. Versions of them. If you look at the practice midterms, so the midterm module has, I can show you. The midterm module has a midterm archive, and it has all of my past midterm exams. If you scroll on to the bottom, you'll see the one from the spring. And it's not exactly that document that I have uploaded in class resources. It's a version of that. What it does is it abbreviates it, so it's still very useful, but it doesn't give you all of the information once it pulls up. So yeah, you'll have it on the midterm. It's a tool for you to be able to utilize, but you have to know how to utilize it. Guys, some tips I give on synthesis, by the way. Map your carbons. Make sure you recognize whether you need to lose or add carbons. Brainstorm reactions. What functional groups do you see in the starting material? What reactions go with them? What functional groups do you see in the products? What reactions make them? And then work forward and backwards. Can you take your starting material and make something new? If you're not sure what direction to go with your starting material, can you take your product and figure out what it came from? Sometimes figuring out what the product came from gives you a better idea of how to get to it from the starting material. So use those tips as you do the synthesis problems. Try to work forward and backwards.
Something you remove something. I just remember it as like you remove it.
I'm thinking that the bromine would leave because it's
So NaNH2, NH2 minus
Right?
is a very strong base.
Strong base. Just
So
strong base?
like tert butoxide will pull off a hydrogen to do an elimination of the bromine, but NH2 will pull off one hydrogen to make an alkene with a bromine, and then pull off another hydrogen to kick off that second bromine and make an alkyne.
So what would it be like? Is it a strong base?
I would say it's not really in that table.
Just no, it takes off.
It's mostly used for making alkynes.
Okay.
So when you see that NH2 minus, you should think alkyne formation.
Would it be two equivalents then?
Right, well, if you have two equivalents, you can pull off two hydrogens, kick off two bromines. But if you have a third equivalence, then you can deprotonate the alkyne,
Oh, so then it's minus.
and then it's a negatively charged alkyne anion.
Which is a strong base, strong.
And I actually don't know if I gave you the...
Sorry, I can make this bigger.
No, it's all good. Did I give you... No. I didn't give you the reaction in that table where... Oh, I showed it here. I showed you that the alkyne anion can be used as a nucleophile. So if you create an alkyne anion, you're probably looking at doing substitution. Great start, Evan. So Jaylee, with this elimination, this base is TBuO minus, tert butoxide, and that base is big and bulky. So in addition to wanting to do elimination, it wants to do elimination from the least substituted or the most accessible position. So it gives us what we call the anti-Zaitsev product. This hydrogen is crowded by all of this steric strain, but this hydrogen has much less steric strain. So tert butoxide favors whatever hydrogen has less hindrance to it. In that first reagent that you used, you introduced bromide, But with an alkane, bromide won't really react. In fact, the only reaction that we have with an alkane, this is the only reaction we have. And I messed up on here. There should be I lost my methyl group. I think when I grabbed it on my thing to copy and paste, I didn't grab the methyl. To get a halogen onto an alkane, we use radical halogenation. We take a halogen and light, and we split that halogen into radicals, and then one halogen takes out a hydrogen, and the other radical halogen slips into the molecule. So we can go from alkane to alkyl halide using radical halogenation and light.
So, is the mass spectrum review like from Ochem 1?
All of it is.
Okay.
But mass spectrum is going to be like one of the smallest parts of our like midterm and final. I always have at least one question on NMR and IR on the midterm and the final. Sometimes I have a question about mass spec. And usually what that question is, it's framed around the molecular ion. So which of these structures is a molecular ion, which of them is not a molecular ion? The molecular ion, if you remember, was losing one electron. We did it, the practice problem yesterday. Yeah.
Where it ends up with one electron, the other one with a positive.
Yeah.
High bond.
An unpaired electron, a positive charge. We call that molecule a radical cation. Otherwise, some of those molecules split apart. The radical ends up on one fragment of the molecule. The cation ends up on one fragment of the molecule. And only the cation gets pulled to the detector. But with the molecular ion, the only way it forms is if the radical and the cation form on the same structure.
Oh, okay. Makes sense.
So that's what I would lean into the most, to be honest. But you'll see it a few times. There's a homework bonus assignment that you can do, and in that assignment, it has some mass spec on it.
Okay.
Yeah, I wouldn't be too stressed.
Okay. Perfect.
If you can do what's on active, you'll be all right.
Okay, thank you.
Mm-hmm. Yes, it is. So is this. This is close. But if I have HBr with my HX, I should expect X to move to the most substituted carbon. In the event that that most substituted carbon rearranges because of the carbocation, it still goes to a more substituted carbon. So actually HBr with this would form this structure again. If I want the X to move to the least substituted carbon, I need my alkene, and I need to put the X on the least substituted position. So I need HX, but I also need peroxide. Peroxide there is another radical initiator. So it makes more radicals for us. And it's the radicals that change the regiochemistry. Great work. Mm-hmm. Okay, guys, that is our time. I'm here until 10 with my Ochem 1 class, so you're welcome to stick around and keep working. Otherwise, unit test opens tomorrow morning. You have until Monday night to finish the unit test. 2 attempts on Part A, 1 attempt on Part B, but make sure you give yourself enough time on Part B to take pictures and upload. If you can't upload your pictures to Part B before the time runs out, post them as a comment as soon as you can or email them to me as soon as you can. I'm happy to accept them. I had a student in the spring that misunderstood that and thought they could have an hour after the time limit to finish working on the test and upload it, which is not what I'm going for. I'll give you some benefit of the doubt because sometimes emails don't come across right away, but try to send me your work as soon as you can after your test closes, if you can't get it in before. Have a good weekend. I'll see some of you guys in lab today. And then you can have a good weekend.
For this one, it's just that the ketone can go on either.
Structural isomerism. Yep, that's it.
Okay, perfect. So it's like,
Oh, Pamela and Esmeralda loaded. So on the version that I was showing you guys, that correlation table had words as well. No more words, just structure. On the IR, it had structures. No more structures, just the words. So still very useful if you know how to use it. You're welcome.